what we did last time. Anybody need one of these from last time? All right, so on the back side, we can either do section 5, 6, or 7. They all use all three equations. But the last one deals with percent yield, and the other ones do not. So should we do the last one? All right, first question. Let me just take a picture of this, and then I don't have to write it down. You guys have it in front of you. Okay, it says, how many grams of HF could be produced in a reaction which also produces 88.5 grams of XE? So if you look at the very top, it says, consider the following reactions when answering the questions for part 5 to 7. So what equation are we going to use? First, second, or third? Second. Does that make sense, guys? So the equation, the second equation, says XEF2 plus H2O yields XE plus HF plus O2. All right, so what's our first step? Balanced equation. We have to have a balanced equation before you can do anything. Well, you don't have to before you can do anything, but since we have to do it anyway, we just as well start there, because every single stoichiometry problem uses it. Good? All right, so where should we begin when balancing? With 1 or 2? 2 is the biggest number, right? It appears 3 times. So what one do you want to start with? The first one? Sure. So, okay, let's do the second one. Okay, H2. There's 2 hydrogens here. So what coefficient goes in front of HF? A 2. All right? And we just changed the fluorines. There's 2 fluorines there. There's 2 fluorines there. So far, so good. 1 xenon, 1 xenon. Okay. 1 oxygen there, 2 oxygens there. So we better do 2 on the left. And what did that just do? Changed my hydrogens to be 4 here, so we better do a 4 there. And then we just changed my fluorines, so we better put a 2 there, and now a 2 there. Y'all with me? So we started with hydrogen. No big deal. We could do it. We had to erase one thing and fix it, but we could still do it, right? Okay. So now let's go ahead and do, now we have this problem. We are looking for how many grams of HF, and we know we have we produced 88.5 grams of XE. Okay, now what do we do? We can use our steps that I gave you last time, or we can use the mole roadmap that you get on every test. What would you rather use? Mole roadmap? Because then you don't have to memorize anything, right? Well, okay. So let me take a picture of this. And you guys all have one? Does anybody need one? You want one? Yeah. And that's just a periodic table you get on the exam. Anybody else need one? Okay. All right. So let's see. We know we have a certain amount of grams of XE. What should we call that on our mole roadmap? Grams of A or grams of B? It doesn't matter, but A comes before B. We start with A. Start with what we know, right? So it makes sense in my mind. We call A XE. I'm going to change this A to be XE as well. Y'all with me? And then what am I looking for? Grams of HF. So instead of grams B, I'm going to change B to be HF. Y'all with me? And you don't have to do this literally, but just kind of imagine what you're doing. If you want to write it down, do it. Okay? And so this is our plan of action. I'm starting with grams of XE because I know how many grams of XE I have. Yeah? And so where can I go from there? The only place I can go, according to this map, is to moles of XE. And how do I do that? Molar mass of XE. It says molar mass of A right there. So we're going to use the molar mass of XE because our A value is XE. You with me? Then once I have moles of XE, I'm trying to get to grams of HF. Where do I go next? Just like reading a map. I know you guys don't use maps anymore. Okay? We use our phones, but there's still maps on our phone, right? There's still, okay, now you go this way, now you go this way. This time Siri's not going to tell us, in 500 feet, turn left. Like, but I didn't bring my measuring tape, I can't. Okay, whatever, right? Okay. So we are going to follow the path that gets us there. We're going to convert moles of XE into moles of HF using what? Coefficients in our balanced equation. That's these numbers right here. Right? And then once we have that, we're going to use the molar mass of HF to convert it to grams of HF. 3 steps. 1, 2, 3. We understand this? Questions? Okay. If we don't understand it, I'm not sure where you don't, so you got to tell me. Please, at least tell me, you know what? I don't get the whole map. Maybe that's it. Or I don't get what these things mean. Okay? So please say something, because if you don't tell me, I promise I can't read your mind. I cannot. Okay. So, and yeah.
Can we, pretend that we have 4 grams of HF and figure out, how much XEF we would need to react with?
Definitely. You want to do it right now?
Yeah.
Okay. So 4 grams of HF, you said?
Yeah.
And you want to know how many grams of XE?
Yeah.
Okay. Are you saying that because this is a 4 right there?
Yeah, it was the first number that came to mind.
Okay. You
We can change
definitely,
anything if you want.
you definitely can. But does this 4 represent in grams? Okay, just to make sure we all know that. Okay. Okay, so 4 grams of HF. And then how do we get to grams of XE? Let's go the opposite direction, right? It's like if you want to go to Las Vegas, you take I-15. Well, that's not the only way. You take I-15 and get to Las Vegas. What if you want to go to Salt Lake from Las Vegas? Well, you take I-15 and go the other direction, right? You go the same way. And that's all we're doing. So whether we go from HF or to XE or XE to HF, it's the same path. You with me?
Yeah.
All right, so now we have 4 grams of HF, and what it tells us to do is use moles of HF, right? Not moles, molar mass of HF. So what is the molar mass of HF?
1.01.
1.008 plus 819, right? So 20.01, sure. You can round, no big deal. But if we don't round, we're going to say 20.008, right? Can you round? Sure. No big deal. Just don't round too much. Okay? Because then your number is going to be even more off of the answer on the multiple choice. Okay? And what goes on top? Molar mass is 20.008 grams per mole. This is a conversion factor. Per 1 mole of HF. Does everybody understand that? Please say something if you don't.
Where did that come from again? That 20.008?
Because we added the atomic mass of hydrogen is 1.008, and we added the atomic mass of fluorine, which was 19. Added those together, and we get 20.008. Make sense?
Yeah.
Okay, thanks for asking. So grams of HF go away. And let's see. Now we're here. We're at moles of HF. That's what we have in our units. And how do we go to moles of XE? And we don't even have to go to XE. We can go to any one of these guys. Any one of them. But just do one at a time, right? And do whatever the question asks. So what is the mole? So now we've got to use the mole to mole ratio from HF to XE for this example. So how many, we want moles of HF to go down here. Do we all understand why?
Yeah.
So the moles of HF go away. How many moles are we going to use? Well, what do we want? What are we trying to go to? Eventually, we want to go to XE, right? Or does everybody lost because we decided to flip it around? So we're not doing the problem at hand yet. We're doing a different one.
I just get lost if, I know we're going to the XC moles on top, but because there's 2 of them, does that matter, or are we just doing the one?
Moles of XE. So when we use the coefficient from our balanced equations, we use the exact coefficient. So what goes in front of XE? How many moles of XE? 2. How many moles of HF? 4. Do you get that?
Okay, that's where my question.
That's it. And that's why that is the only reason why we use the balance equation. It's why we balance our equations. Yeah.
Can't you reduce that to like?
You can.
Okay.
You definitely can. But let's just let our calculator do it, right? Because we're going to multiply and divide when we're done anyway. But you definitely can. But I wouldn't. I would just keep it as is, and then let your calculator do all the math or the arithmetic, okay? So moles of H2 or moles of HF go away. Now we have moles of Xe, but we're looking for grams of Xe, right? So now we got to use the molar mass of Xe. Well, what is the molar mass of Xe? Molar mass of Xe. 133? 131.3 grams per mole. And so moles of Xe go on bottom. How many? If we have 1, we know the mass is 131.3 grams. Now, since we're dealing with Xe, do we have to multiply that by 2? If we want to do it for 2 moles, we do. But what's given on the periodic table is for 1 mole. So don't multiply anything. If you do, you have to say it's for 2 moles or for 4 moles or whatever the coefficient is. Guys, let's just keep it simple.
Isn't that why you would like want to reduce it in the middle?
And you can. You definitely can. Why would you want to reduce it and simplify it mathematically if you don't have to?
I don't understand how it simplifies it.
With the calculator?
Yeah.
Okay. Because if we do 2 divided by 4, what do we get?
2.
1/2.
Yeah, that is how math works.
Right? So this 2 cancels and we get a 2 there. So we can multiply by 1/2 or we can divide by 2. Is that the same thing mathematically? It is.
Yeah.
And that's why don't worry about simplifying our conversions. Don't. Leave them there and let our calculator do it. Make sense? Glad you asked.
I'm really bad at math.
That's okay. No big deal. So we just got to learn how to use our calculator so it can do it for us, right?
No, dude, I learned Excel and just like everything left after that.
All right. So now moles of Xe go away and we're left with grams of Xe. Now we just multiply what's on top, divide what's on bottom. Does it matter the order? It really doesn't. It really does not. I like to do it from left to right. So me personally, I do 4 divided by 20.008, multiply 2, divide 4, multiply 131.3. That's me. If you want to go back to 6th grade, when we learned how fractions worked, then we can multiply all the tops and get an answer. We can multiply all the bottoms and get a different answer. And then divide them. We could. But if we're using a calculator, then I don't want to have to type some numbers in and write a number. Type some more numbers in and write another number. And then divide those numbers. That's too much work. So I like to just take the top number, multiply the top numbers, and divide the bottom numbers from left to right as I read. And then I don't have to go back, which one did I miss? Right? Just go in order. Is the simplest, but that's me, guys. That is me. You don't have to do it the way I do it. But you do have to do it a correct method. Okay?
Yeah.
And so that's what I teach. You with me? All right. And we get an answer. Do you care about what the answer is?
Have I come up with it?
Because I don't have it. But
I don't
if you don't care, we can just move on to the problem at hand.
Yeah, just move on. 13.1247.
13.1247? 1247, let's just say 1. Okay. All right, and that's grams of Xe. Good? And we can be given it any amount doesn't matter. The process is the same. And now let's do the problem at hand. Is right here. So I'm going to start with what I was given, because I know that's true. So I'm going to start with 88.5 grams of Xe. And I don't want grams of Xe, so I follow my mole roadmap here, and it says, okay, go to moles of Xe using the molar mass of Xe, which is 131.3. That goes on bottom, 131.3 grams of Xe to every 1 mole of Xe. That goes away. And now I'm right here. Now I can use the mole-to-mole ratio to go to moles of HF. And I know the ratio is 2 to 4 by my coefficients. So what goes on bottom? 2 moles of Xe. Does everybody understand why 2 moles of Xe? Because that's the coefficient in front of Xe. And why Xe? So that Xe can cancel out, because we don't want that in our answer. And what goes on top is what we're looking for. 4 moles of, we're not looking for 4 moles of HF, but that's 4 is our coefficient in front of what we're looking for. Are we good? And we want grams because our question says how many grams of HF. So now we're here, and we got to go to here using molar mass of HF, which is 20.008. So what goes on bottom? What don't we want? Moles of HF, and we want to go to grams of HF. So how many moles do we know the mass of? 1 mole has a mass of 20.008 grams. Y'all with me? And you multiply and divide all that stuff, and we get 27.0 grams of HF. How are we feeling? Better? Still bad? Okay. Slightly better, that just means what? We need more practice. So don't forget to do these at home. Use AI to help you, not to get answers, but to help you. Yeah.
I actually have a note on that. We get Gemini Pro free with our student whatever.
Uh-huh.
You should have gotten an email about it. And then like if you click the little guided learning thing, it tutors you like a dumbass, and it's really helpful.
Oh, heck yeah.
Yeah.
You got
Gemini Pro. Yeah.
and it's just on your PC computer?
Yeah, it's just in your browser.
Okay.
If you go to like your Slick email, like on your Canvas email, and then search for it, I'm sure everyone got it. It's been helpful.
Does it work for Apple users?
Oh, it's in your browser, yeah.
Okay. Like it's a website?
Yeah.
Okay, perfect.
I'm sure there's an app too. I don't know. I'm not an app user.
Okay. And there's all sorts of AIs out there, guys. Maybe maybe that one's a good. I'm not sure which one's the best. I haven't used it enough, or very many of them. So, yeah, just find one and see how it works for you. Yeah.
I get how to do everything after you balance it, but from just reading it, how can you tell how you set it up basically? Like,
Okay.
like how do you get HTML?
Okay. Good. Great. Love that. Should we do the next one and try it again, so we don't have to repeat the same thing? Does that sound good? All right, just erase that so we can read it. Okay, so let's start with, so it says, how many grams of HCl can be produced? So grams of HCl, that's my question mark. Just like when we did problem-solving strategy before. You guys understand the problem-solving strategy I taught you? Okay, so what is the question with units? So we got to know what that is. We want to know how many grams of HCl. And if you want, you can write that out. Grams of HCl equals question mark. Whatever helps you, okay? I'm just going to underline it so that I save room. But guys, do what you need, okay? And then it says, can be produced by the reaction of 59.25 grams of PCl3. So what is it that I know? 59.25 grams of PCl3. That's a known value. You with me? Okay. All right. So, what do I do?
We're gonna use the first equation.
What's my first step? Balance the equation. Oh, I don't even have an equation, do I? Oh. If you look at the top of this page, it says these equations are used for these problems. And on the test, on the exam, I will give you the equation. Okay? Unless it's one that's talking about predict their products from chapter 5, right? Using double replacement reactions, right? Okay? I might ask you to do that, but in stoichiometry problems, yeah, I'm going to say, okay, here's the equation. Now figure this out. Okay? So our equation, should I erase this or should I? It's getting kind of messy here, isn't it? I'll write it down here. So we got, what equation are we going to use for this problem? The first one. Does everybody understand that? Because we're dealing with PCl3, so use the one with PCl3 in it. So we got PCl3, that's kind of hard to read, huh? PCl3 plus H2O gives us H3PO3 plus HCl. Okay, what should I do before I start the problem? Balance it. Okay, so we have a bunch of 3's. I'm going to deal with hydrogen last because it's everywhere. Three of those, so I'm going to put a 3 right here. I have 3 oxygens, so I'm going to put a 3 right there. Y'all with me? Now I'm going to count my hydrogens. I have 3 here and 3 there. That's 6. Oh, good. That worked out. Done. And there's 1 phosphorus, 1 phosphorus. Everything's accounted for. We're good? And if we have a hard time with that, then get some more practice on balancing equations. You can ask AI to produce you more examples, or you could just type in Google, say, hey, give me a worksheet to help me practice balancing equations. And hey, include answers so that I know if I'm doing this right. Right? And just know that no matter what you get, there could be some errors, right? Whether it's on AI or just in Google, there could be errors. So if you think, oh my gosh, how is it even getting this? Don't throw everything else, okay, I quit, right? Just know that there could be some errors. All right. All right, so now we have a balanced equation. Now, is it going to confuse anybody if I scroll back and forth to this balanced equation? So if I come up here, do the problem, Oh, I need my balanced equations to come up here. Does that confuse anybody? Or should I copy what I have up there to move down? Should I do that? Okay. Copy. Paste. Oh. It's okay. Calm down. Okay, here we go. So I'm looking for grams of HCl, and I know I have 59.2 grams of PCl3. And I have my balanced equation. So now let me also clear this board. And let's copy it. Paste. There we go. How we feel about using the mole roadmap yet? We okay, or is it still like, what does that even mean? If you want to just use the steps I give you, that works too. All right. So let's begin. So you said, how do you know what to do, right? Is that the question? Do you understand what to get the balanced equation? You said you understood that?
No, I just didn't realize the equations were up here.
Oh, okay.
Confused for me.
Oh, was that the only problem?
Yeah.
Okay. All right, so where are we going to start, guys, after we have a balanced equation? With what we know. This 59.25 grams of PCl3. Do you want to use the mole roadmap again, guys? Yeah? Let's do it. I start with grams of PCl3. Should I say that's grams of A? Okay? So this is where I'm starting, and I don't have to write it. I just know where I'm starting. And I want to go to grams of something different. So I'm going to go to grams of B. I'm going to start here and end here. How do I get there? I follow that path. 3 steps. 1, 2, 3. You with me? And so my first step is I use the molar mass of A as my first substance of PCl3. So I find the molar mass of PCl3, which is, phosphorus is 30.9 something? 97. Plus, chlorine is 35.45. And don't forget to multiply that by 3. And I get 37? 32 grams per mole. Y'all with me? Y'all understand how I got those numbers? Okay, you don't have to memorize these numbers. Look at the periodic table. That's where they're coming from. All right. So grams goes on the bottom, so we have 137.32 grams. And why does grams go on bottom? So they cancel out. Perfect. To how many moles on top? 1 mole of the same substance. This gives us to moles of that same substance, PCl3. You with me so far? Okay? So grams, PCl3 go away. And now I'm here. And now I got to go to moles of B. Moles of, in this case, HCl is my B, right? Using the coefficients of my balanced equation. So here's the coefficients. I'm going from PCl3 to HCl. PCl3 has a number of 1. HCl has a number of 3 in front of it. So what goes on bottom, 1 or 3? 1, because we want moles of PCl3 to go away. You with me? So 1 mole of PCl3 on bottom. And what we're looking for is HCl, so 3 moles of HCl. Does anybody have any questions on that step? When we see those units cancel out, moles of PCl3, that tells us we're doing the right thing. And we want grams of HCl, so we got to keep going. On our mole roadmap, we're right here. So now we just use the molar mass to get to grams. Molar mass of HCl is 1.008 plus 35.45. That's a total of 36.458. Okay? Grams per mole. We want grams, so the 36.458 grams goes on top to 1 mole on bottom. We good? And we do that, we do all the calculations, we multiply all the tops, divide all the bottoms, and we get 47.19 grams of HCl. Now, if we go to the lab, is this what we get? In theory, if everything goes 100% correctly, and we make perfect measurements, this is what we should get. This is our theoretical yield. You with me? Then the next question says, if the reaction above only produces 37.552 grams, what does that mean, only produces? We go to the lab and this is what we get. What do we call this? This is our actual yield. We go to the lab, we do this, and we only get 32.52. So we want to know what the percent is. How did we do? Just like on a test or a quiz, how did we do? What's our percentage? What we got right, our actual yield, 37.52 grams of this is HCl. How do we know? Because it says the reaction above. And what we're trying to get is our theoretical yield. So this is the total, 47.19 grams of HCl. What cancels? Grams of HCl. And how do we convert that to a percentage? Times 100%. And we get 79.5% yield. Good? Not very good, is it? 70, that's average, right? But hopefully we don't want average. Okay. Any questions on stoichiometry? This is the summary of what we learned in chapter 6 last time. Was that worth it or was that a waste of time? Good, good. Are there any questions before we move on to chapter 7? Yeah.
This is my lack of understanding of math, but how would you get the same answer multiplying all the top in the thing rather than doing the way we do it?
So multiplying all the top, then dividing all the bottom, then dividing the,
Yeah.
or sorry, multiplying all the top, get an answer. Multiply all the bottom, get an answer, and then divide them.
Yeah,
Why is that the same?
yeah.
We can
You
have
don't
a,
have to spend
we can
time.
have a whole proof and talking about why this is true. Do you have an easy answer?
Yeah, I think, cause you're just like multiplying by 3, like one part, at least the way I do it is I multiply by 3 at the end. You're just doing that like one step earlier. Like, I got like the moles to moles and then I multiply by 3 at the end. I think you're just multiplying things a little bit earlier and then putting them at the top of the denominator.
So, yeah, if we have 3 over 4 multiply 2, what do I do first? Now, in your head, you might say, oh, I'm going to just do that, right?
Yeah.
And then I get 3/2 or 1.5. That's one way to do it. My answer should always be 1.5. Now let's multiply the top and I get 6, and the bottom is still 4. I can use a calculator and it'll still give me 1.5. Or I can do 3 divide 4 and get 0.75, and then times 2. And what do I get? 1.5. Because we're doing the same thing, just in a, like he said, in a different order. And order of operation for multiply and divide is the same thing. If we're multiplying, divide, and adding and subtracting, we gotta. And why do we have to keep it separate? Why do we have to do it in a certain order? So that we all get the same answer. I see things on Facebook. Check this out, guys. Math is stupid. And it says, look at this. I typed this in and I get two calculators. I get different answers. Because we have an order of operation because, or so that we all get the same answer. That is why. It's man-made. So that we're all on the same page. When someone from Russia does a calculation, someone from Australia does a calculation, we all get the same answer. Okay? Did I help or no?
I like the idea of you having to prove multiplication, division being the same in this class period.
Heck yeah.
I'm sorry, I'm sorry.
No, don't be. If you have a question, ask. Because if we get all the chemistry down, but we can't do the math, it's like, ooh, then,
I mean, that's my thing, like,
right?
I'm good at getting the answer for all this stuff, I just don't understand the math that's like happening in between.
All right.
But I'm getting there, I'm getting there.
Did it help or still kind of in?
I'm gonna just keep doing it the way I've been doing it.
Okay.
But yeah. Yeah.
All right, let's move. Any other question before we move on to chapter 7? Okay. So we didn't get very far in my last class, so we're not gonna cruise through this. I had one of my students from last class says, "Oh, you're teaching like a Ferrari last time." Is that what it felt like? Okay, we're gonna do Prius style today. How's that? All right. So chapter 7 is thermodynamics. What is thermodynamics? Ooh, that sounds scary.
Physics.
Yeah, it's just physics.
This is chemistry.
Which is? Physics
Don't,
matter.
I don't wanna hear it, I don't wanna.
All right. So thermodynamics is basically, what's thermo mean?
Temper.
Yeah, heat, right? We're dealing with heat. So it explains why chemical reactions occur. Or not occur. Explains why or why not chemical reactions occur. So, I wonder if I'd have I'm gonna start with just enthalpy and do one at a time, and we'll go as much as we can with one, and then I'll talk about the other, rather than giving you all the definitions and then wait for a day or a week or whatever, okay? All right, so you guys are a little bit luckier because I went through this once, and I kind of, okay, maybe I should do it a little bit different, right? So now you guys get the better version. Okay. Sorry, my other class that's listening on this. Okay. All right. So enthalpy is the first term that we're going to deal with. That sounds yummy, right? No. All right. So enthalpy is heat energy. And there's, I don't know, just a way to remember it. I don't know if this is a good way. If you don't like it, throw it out. But there's an H in the word enthalpy. And H stands for heat. So heat energy, released or absorbed in a physical or chemical process. And the symbol we use for enthalpy is delta H. You guys all know what the triangle means, the delta symbol? Change in, right? Because we're changing, we're releasing or absorbing heat. That means our amount of heat is changing, right? We're either getting more of it or getting less of it. And so that's what we use for enthalpy, delta H. And there's two versions. When delta H is negative, so if we lose energy or release, a release of energy, this is called exothermic. Exothermic means a release of heat. Good? Does it make sense why we have a negative delta H? Because it's exiting. We're losing it. Losing means minus, right? Good? And an example of this is gasoline, C8H18. If we burn it in the presence of oxygen, we have to have oxygen to burn it. What do we get? Can anybody tell me? Water and carbon dioxide every time. This is a combustion reaction. Can you all recognize that? Okay. All right, is this an exothermic or endothermic reaction? I didn't talk about endothermic. This is exothermic. We know this is exothermic, right? We all deal with burning gas. You guys ever do a campfire and having a hard time start it? Go grab some gas, right? Just don't grab the whole tank and start no, don't do that. Get a little bit of gas, right? Pour it on the area you want to light it, and then light it, okay? Or just be careful. But we know what happens when you burn gas. What happens? We get a lot of heat coming at us, right? So heat is exiting our system. So it's being released. We got exothermic. Make sense? So when we say that, if heat is being released, is heat a reactant or a product? Product. We get it in the end, right? So we're going to say plus heat over here. That also tells us it's exothermic. If we have a negative delta H or a negative enthalpy, we have exothermic. Or if the amount of heat energy is on the product side, we have exothermic. Good? Questions on that? Why don't we put minus right there? Because it's heat. Can you have negative heat, guys? No, in real life, it's just heat. When we burn this, we're getting heat come at us. Oh, I'm getting heat. This is my product. So whenever I have something in my chemical reaction, it's always separated by plus signs. Always. Never by a minus sign. Good? Yeah.
On the worksheet in question 2, there is a minus sign. It's like delta H equals negative 44.5 kilocalories.
Yeah. So that's not in the reaction, though. That's saying the delta H is a negative value. So what does that mean? Is it exothermic? Yes. That's what that means. Good. And we'll talk more about it when we get into the other version. Okay? And then we'll also do, we'll kind of bring all of this and do some stoichiometry with it. Are you guys excited? Woo, yay! Okay. We'll get there. We'll get there. All right. So, but let's talk about what's going on here. So if I draw the structure of C8H18, this is gasoline, it's going to look something like this. 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. And then you got all of these hydrogens. 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3. There's my structure. The H's are hydrogen bonded, and all the little endpoints are carbons. You with me? It's just a lot easier to draw it that way than to draw all the carbons and all the hydrogens and yuck. You with me? Okay. And I won't test you on this. I'm just showing you a quick way to do it. If you want to use this, you take organic chemistry, okay? Please let me. Okay. So, what do we have in here? In each one of these bonds, they're storing energy. You guys ever heard of potential energy? Potential energy is stored energy. And when something is stored, it means it's not being used, right? Okay, we go to buy a storage unit and pay so many dollars a month, and then 10 years later, I'll just throw it away, right? How many times do we do that? Oh, no, never. Okay. But stored, we don't use it. But it can be used whenever we want, right? So in these bonds, we have a gallon of gas can just sit there for a while, right? I mean, it'll evaporate if it's too hot, but it'll just sit there and nothing really happens. We can use that later if we want. It's stored energy. It's in our gas tank. We're not using it yet. As soon as we start that engine, then we start burning it, right? But what happens is when we have, if we're in the presence of oxygen and we give it a little teeny spark, then what happens is all of those bonds break down. A couple of them form to make water and carbon dioxide, but most of them are broken. And so we get all that energy, and we can't just get rid of it and destroy it. It goes out as heat. Does that make sense? Okay. Any questions on exothermic? Okay? The other type is endothermic. Endothermic means heat is absorbed in the reaction. And this could be physical or chemical process, okay? And we say endothermic is a positive delta H. Because absorbed, we have to take in energy. We have to get energy before we can make this reaction happen. That kind of makes sense? Okay, so let's do an example here. We did this reaction already. We have solid magnesium in the presence of oxygen gas. And if we give it heat, so we add heat to this. Remember when we did this? We had a strip of magnesium and we burned it and it got real bright. Okay. And we're going to get magnesium oxide. Solid magnesium oxide. So this is endothermic. We have to take in the heat to make this reaction happen. We're not breaking any bonds, are we? We're forming bonds. So it takes energy. We good? All right, so let's talk about even more simple physics here. If we have a ball and it's just sitting there, it has stored energy, right? Has potential energy. It's not doing anything yet. We give it a little bump, and then what happens? It comes down here. It starts rolling down. Turns into what? Kinetic energy. Energy of motion, right? So potential energy turns into kinetic energy. And kinetic energy is energy of motion. What kind of energy is heat? It's also kinetic. When you move things, what happens? Hotter and hotter and hotter, right? The faster you move it, it gets even hotter, right? Or if things get hotter, they start moving faster. We get that idea? Okay? And so when a ball rolls down a hill, what is that? Exothermic or endothermic? Exothermic. We're changing that potential energy, the bonds, and we're breaking those bonds and releasing it into kinetic energy or heat, right? Okay. What if we go up the hill? We have to give it the energy to get to where we want to go, right? That's endothermic. We have to absorb that heat. Yeah.
So we are absorbing heat, but isn't heat also like generated from the friction of pushing it up? Is it like a...
Yeah, we're using this scenario just to keep it simple.
Oh.
Yes, there's friction involved, and we're not going to get there. That's more physics.
But my main question is like the heat lost, heat gain thing, it's just like you add together all the different heat that was lost?
Yes. Perfect. So, like in this other example, are bonds formed? They are. So it takes some of that energy to form those bonds, but mostly we break bonds, right? And so the net energy is released. Good question. Is that what you was asking? Okay.
So I have a question.
Uh-huh.
How you wrote in your reaction, why wouldn't the heat be over the arrow?
Sometimes they put it there.
Okay.
You have a change in heat. So sometimes when they write it like this.
So it means the same
But this doesn't tell us what's happening to the heat, whether it's released or absorbed. It just says we have a change in energy, right? And that's true. But when we put it right here, we take it in, we absorb it, and when we put it on the product side, we release it. Does that make sense? So a little bit more detail to write it this way. Uh-huh. All right, so let's start with some simple examples. Some examples that we're familiar with. So let's start with H2O as a liquid going to form H2O as a solid. What do we call this process?
Freezing.
Freezing. Liquid to solid. We're freezing water, right? Okay. So what do you think? Is this an exothermic or endothermic reaction? And to be able to answer this, you have to think about where that heat is coming from and where is it going, or vice versa. So I'm hearing exothermic. Do we have to get rid of heat in order to get solid ice? Yeah. We have to lose that heat. Okay? So we can say, okay, let me just put some numbers here to kind of make it a little bit more clear. So we're going to say delta H is equal to a positive or negative value. We have to release the heat. We have to get rid of the heat from the liquid water. So it's a negative, and I'm going to give you this value. You don't have to memorize it. 603 kilojoules. Is it 603 or 6.03? I can't remember. 6.03. Okay?
It's not something we have to remember?
No. Nope. I will give you this value. Right? Okay? What's another way to write this? With just one equation. H2O is a liquid. Arrow. H2O is a solid plus 6.03 kilojoules. Do you get that, guys? Because it's exothermic, because it's a negative delta H, that means we're releasing heat. That means heat has to be on the product side. Are we good? Okay.
So like if you were to ask us the delta H for, if you were to only give us like what you have in white and you were to ask us the delta H, we'd have to put negative 6.03
Yeah.
instead of just writing.
And I probably won't ask that, but yes. What if we flip it? So now we have H2O as a solid going to H2O as a liquid. How would we write that equation now? H2O as a solid plus 6.03. And this time, delta H is a positive value because we flipped it. We reversed it, right? Kilojoules goes to H2O as a liquid. Because we have to take in heat to melt the ice, right? How are we feeling on these simple examples? Okay? When I say simple, I'm not saying easy. It's just not complex, that's all. Okay? Any questions so far?
Can you say it again, why in example 2, the 6.03 are in the middle?
Because this is the same equation, just flipped. So because it's flipped, that delta H is now a positive 6.03 kilojoules. And so what was your question? Was that it?
Yeah, like I just want to understand how I know
Where to put it? Okay. If it's an exothermic, so how do we know it's exothermic? We can use our thinker and says, okay, You have to, no, I'm just saying, there's a lot of different ways. This is one way. If we start with liquid water and we end with solid, oh, we're getting rid of the heat, right? The heat is exiting the system. Okay, that tells us it's exothermic. What's another thing that tells us it's exothermic? Delta H is a negative value. And another way, a third way, is the heat is a product. So we can write all of those down. Exothermic means a negative delta H. It means heat as a product. Good? And endothermic means a positive delta H, or heat as a reactant.
So it's from the context of the system.
Yeah. So, and you can memorize that, you can, but I like to think about why it is what it is, and then it helps you to, but no, do that. Memorize it, but also think about why it is what it is. Okay? Any other questions on endothermic versus exothermic? All right, let's think about something maybe in everyday life. Y'all have a refrigerator, right? You guys ever take the refrigerator away from the wall to clean all the yuck out of there? And if you don't do it very often, then it's like, "Ew." Okay. But you ever put your hand by there's a fan blowing back there, right? You ever put your hand by it? What does it feel like? It's hot. Why? Heat is exiting the system because we're making the stuff in the fridge cold. We're taking the heat out of the food and shoving it outside the refrigerator. And you guys have an AC unit at home? You ever go by on a hot day and you feel there's a fan, that's going to be nice, and ooh, it's warm, right? Might not be as hot as the refrigerator, but it's not cool. It's like, never mind. But that's what's happening, is taking the heat out of your home and putting it in the environment. Exothermic. Make sense? Okay? All right, let's do a real example, like chemistry. You guys want to do chemistry? Whether you want to or not, we're doing it. Okay, I'm sorry. All right, so let's do an example here. So we got 2H2 plus O2, and it forms 2H2O, so this is balanced for us, plus 572 kilojoules. Exothermic or endothermic, guys?
And
Exothermic.
How do we know it's exothermic?
Just the heat is the product.
Heat is the product. We're getting heat out. You with me? Okay. And so that means delta H equals what? Negative 572 kilojoules. Good? We don't have to have both of those, one or the other. Okay? But this one right here sets us up to do calculations. And that's what we're going to do in this class. Okay? So let's do an example from here. Well, this example. So how much heat is released by burning 48.1 grams of hydrogen gas? We have a balanced equation. That step's done. Make sure we always do that. This is stoichiometry, guys. Still doing it. And we're going to do it for the rest of the semester. Okay? So, where do we start now? With what we know. What are we looking for? How much heat? That's our question. How much heat is released? Okay, yeah. This is exothermic. Released means exothermic. Few keywords that tells us it's exothermic. Okay? So we're going to start with what we know. 48.1 grams of H2. What can we convert grams to, guys? Moles. Using the mole roadmap. If we start at grams of A, the only thing we can do is convert to moles of A. Using the molar mass of hydrogen gas is 2.016 grams of H2. Does everybody understand where I got that number? It's just the molar mass of H2. There's 2 hydrogens, so we add the atomic mass of hydrogen by 2 to 1 mole of H2. You with me? And you can use the molar map, the mole road map if you'd like. Okay. Now we have moles of H2. What can we convert it to? Either particles of H2 or something else, right? Well, can we use our balanced equation coefficients and convert it to something else? What are we looking for here? Heat. Can we convert it to heat? Yeah, what's the ratio? 2 moles of hydrogen to 572 kilojoules of heat. 1 mole of oxygen to 572 kilojoules of heat. 2 moles of water to 572 kilojoules of heat. It's the mole to mole ratio. Same as we did in chapter 6. You with me? Okay. So we're going to multiply. We don't want moles of hydrogen, so that's going to be on the bottom. How many moles? 2 moles of hydrogen. To what goes on top? What are we looking for? 572 kilojoules. Moles goes away, we're left with kilojoules, and that's what we're looking for. So we do 48.1, divide 2.016, multiply 572, divide 2, and we get 6,824 kilojoules released. Released. Okay? Well, we can also say delta H, no, I don't want to do that. We'll just say that. Or we can say we have a value of negative 6,824 kilojoules. That also says it's released, right? So most cases we'll just keep it positive and just tack on the word released. Or if it's a positive, if it's endothermic, we'll say it's absorbed. Good?
Yep.
Yeah. Okay. One more example, and if you guys want to keep going, that's one more example, and then we ended in my first class.
No, let's keep going. Speaking for myself.
It's up to you guys. One person said keep going.
I'm not
2
broken
people.
yet.
Okay?
You still sound juicy.
All right. This is fun, huh? Oh. Okay.
That makes this fun.
Would you use, when you write it out, would you use delta H equals negative?
No. No. Because, I mean, I guess you could. I just didn't want to get it confused with this delta H, right? So we'll just say it is 6,824 kilojoules released. All right, let's do another example. So we have a hydrogen tank. No, we don't, but pretend. We have a hydrogen tank. Ooh, that'd be fun. We want to fill with 2 liters of hydrogen gas. And we know the density is 1.293 grams per liter. We want to know how much energy is required to make 2 liters of hydrogen gas. And what else do I need to give you? An equation, right? We have to have an equation. So 2H2O plus 572 kilojoules gives us 2H2 plus O2. What kind of reaction is this? Endothermic, because we have, so this is the same reaction as the previous one, just flipped, right? Okay. So we have to get that energy so we could break these bonds, right? Well, I thought broken bonds means you release energy. Depends on what we're dealing with. Okay? All right, so where do we start? We have a balanced equation. Start with what we know. We need 2 liters of hydrogen gas, right? We also know the density of hydrogen gas. And what are we looking for? How much energy? That's my question. Energy is measured in joules, okay, or kilojoules. So where do you want to start? We know 2 things. Well, we really don't want to start.
Start with the heat.
Start with what?
The heat.
We could, but we don't know how much heat we have. That's what we're looking for, right? Okay, so that's what we want to end with, yeah.
Find how many moles of H2O are in the 2 liter.
Well, so let's start with 2 liters, right? You either start with 2 liters or our density. Those are our 2 known values. Don't start with what you don't know. Start with what you know, right? Okay. And what's easier to start with, 2 liters or density, 1.293 grams per liter? You know, liters. This is just a conversion, right?
Yeah.
Okay, yeah,
So we need to balance the equation first.
it is.
Oh, it's not.
It's not?
Oh.
Yes, it is.
Yeah. And so I just took the same one from the, just flipped it.
Yep.
Yeah.
Yeah, I'm not.
But no, always check. That's important. You have to have a balanced equation, so check. Even if it looks like it's balanced, even if there's coefficients, oh, it's already balanced. Check it, right? Especially if AI is generating the, okay? Always check it. All right, so we're going to start with 2 liters of hydrogen gas. And before we can figure out how much energy, we got to know how many what? Moles, right? We got to get that center of the mole roadmap. We got to get the moles before anything else. So what can we convert liters into? We have the density, so we can convert it into grams. So we got 1.293 2.3 grams of hydrogen gas per how many liters? 1 liter. Y'all with me? So liters goes away. And now I have grams, and now I can really start the mole roadmap. Convert grams into moles. And this is the same one we did in the last one. 2.016 grams of H2 to 1 mole of H2. Y'all with me, or am I going too quickly? We still doing Prius style? Okay. So grams of H2 go away. And I want to know how much energy. So now what? What goes on bottom? How many?
2 mole H2.
2 moles, because that's the coefficient in front of H2. We want H2 to cancel. 2 moles of H2 and 572 kilojoules of heat. That's it. And we get 367 kilojoules of heat is required. Or is absorbed. Do you see that they're two different words means the same thing? Okay. How are we feeling? Like we can rule the world? Or like we can have a good night's rest? I don't care, whatever you want to do.
Aren't hydrogen,
Keep going.
Okay? That's all I heard, so we're gonna do that. Yeah.
aren't hydrogen and oxygen rocket fuel?
Yeah. Well, yeah.
Yeah.
Yeah. Uh-huh.
Just to reinforce previous stuff, I think we talked about this, like butane stuff is a good fuel because it has a lot of hydrogen bonds and a low London dispersion, so it's easy to like break them up and then.
Butane, you said?
Butane, gas, all the
Uh-huh.
C's, lots of C's,
Yeah.
lots of H's.
Yeah. Make sense, everybody? Okay. Let's do entropy, and then we'll stop after entropy. Because I do have to have something to teach you next time. No, we really have 2 times before the exam, so unless you guys just want to hurry up and take the exam. I'm just teasing. All right. Any questions on enthalpy? All right, entropy. Sounds similar. Entropy is the measure of disorder in a system. In a physical or chemical system, either one. In a system. And the S in disorder, since entropy is the measure of disorder, we call entropy, the symbol is delta S. That's not Y, but somebody else looked it up and it didn't make sense why, so we'll just use that. Okay? Now, in nature, things tend to go toward more disorder. So let's think about this for a minute. You ever live by somebody that moves out? Or see a house that somebody moved out of? It just goes downhill real fast, doesn't it? It takes energy to keep it maintained, doesn't it? Okay? And if you don't introduce that energy, it goes to chaos or disorder. You with me? Okay. So, and this part, you really have to think about it, or you can make a simple mistake here, okay? So we have positive delta S as increasing, what's delta S stand for? Disorder, the measure of disorder. So positive, increasing, right? Positive sounds like increasing, right? Increasing disorder. Now that sounds like a negative thing, disorder, right?
Yeah.
It's making it less cool, less wonderful. But it's increasing the disorder. So we call it positive delta S. Do you see how this might confuse you? So you got to just be careful, okay? So just remember, delta S is the measure of disorder. So positive is increasing disorder. Good? And the flip version, negative delta S is decreasing disorder.
Do we have names for them?
No. Rather than saying negative delta S is increasing order, you see how that's the same thing? But just leave it as increasing disorder is positive delta S, decreasing disorder is negative delta S. But you have to understand what that word means, decreasing disorder. It means more order, right? Do you get that? Okay. So let's start simple again. Any questions on the term entropy? Okay. So let's start with an example, simple example again. In fact, we're going to do the same ones we just used. H2O as a solid going to H2O as a liquid. So we're melting ice. Are we going to increasing disorder or decreasing disorder? Increasing disorder, because we start with solid, which is, here's our solid, right? You remember drawing a solid? Going to something that's a little bit less, right? Or a little bit less ordered. So it goes a little bit more disorder. Yeah.
Okay.
So increases in disorder, so this is positive or negative delta S?
Positive.
Positive delta S. We good? And if we flipped it around, obviously, well, I shouldn't say obviously, goes from liquid to solid, goes to more order, so decreasing disorder. Good? Yeah. Okay, example 2. If we have C8H18 plus O2 gives us CO2 and H2O. So this is burning gasoline. Can we tell if that's disorder or order? Increasing disorder or decreasing disorder? How? Three different ways we can just think about it. All of them you can't. Because we know what happens when we burn gas. We know what happens. But do we know all reactions? No, most of them say, I don't even know what that is, right? Okay. But this one, if we think about it, do you think burning gas increases disorder or decreases disorder? Increases disorder. It just blows everything up, right? And just makes everything chaos. Okay? Here's how you tell with just an equation. First of all, you have to balance it. Well, that's good. We have to balance equations anyway. Okay, so let's balance this. So we have 8 carbons there. We're going to put an 8. 18 hydrogens. We're going to put a 9. You following me so far? Am I going too fast? Okay. And now we're going to count the oxygens. We have 16 here. And we have 9 here. That's a total of 25. Is that 25?
Yeah.
25. How do we get 25 here? Oh, 25 halves, right? And then just multiply everything by 2. Remember this? So we're going to put a 2 there. Let's just change that to a 16. Change that to an 18. Just multiplying everything by 2. And now we have 16 times 2. That's 32. And 18. And that makes 40, 50. Yay! All right. So just like we did with this, we have particles that are all combined, right? 2 particles that are just a little bit more spread out. How many particles do we have? We can call these moles, or we can call them particles, can't we? Do you see how we can interchange those? Because of 1 mole is the same number of particles of any substance. Okay? So we have 2 particles and 25 particles. That's a total of 27 particles on the left. How many on the right? 10, 20, 34. Which one's more chaotic? The 34 side, right? There's more particles. It makes it more chaos, more disorder. So this is positive delta S. Do you follow? Well, we already knew that with this one because it's gas. It just throws everything out, right? Y'all with me? So that's the easiest way to figure out entropy, the measure of disorder, is by balancing the equation and then counting the particles. Good? Let's try another one. Or do you have any questions?
Isn't heat also a pretty low order energy?
Yeah, because it's moving so
Yeah.
fast. Because, yeah.
So you could also kind of look at it like that sometimes. Yeah.
All right. So we have 2H2 plus O2 gives us 2H2O. I already balanced it for you because we've been using this equation a few times. Positive delta S or negative delta S? Are we increasing disorder or decreasing disorder? Decreasing disorder. We're going from 3 particles to 2 particles. Or decreasing disorder, so this is a negative delta S. Good? Okay, that's funny. This is the same time we ended in my last class. I think it's a sign. We should end. We're done with entropy. Unless you guys have, in fact, you guys have a worksheet here. We didn't do anything on that worksheet. I always forget to do that. Do you guys have any questions on the worksheet? So far we did predict whether the following process absorb heat or release heat. That's exothermic and endothermic. And then use a little bit of stoichiometry in section 2. And then section 3 is determine whether something is more order or more disorder. And you can change that to be more disorder, increasing disorder, or decreasing disorder, right? So just be careful with that. And then we didn't learn section 4 yet.
Would it be okay if I advertise like a club event?
Go for it, yeah.
Okay. The psychology and sci beta